continuing our discussion that we have been having about integral equations, what we looked at was a simple static case, electrostatics problem, and we found out the charge distribution. Now, we will begin to move into the area of electrodynamics, where there is a time varying field as well, because that is the main kind of problems that we are interested in this course. So, what you looked at was a very simple kind of integral equation. Now, we will try to make things a little bit more interesting. So, these are the topics that we will cover in this module. We will start with some physical intuition about how and where waves seem to bend. Okay. That sets up the motivation, and from there we will see how the this idea leads us to what is called the Helmholtz equation and ways of solving the integral equations that come. Okay. So, let us just start with the idea of waves that are bending. Right. So, let us start with this simple idea of mobile reception in a room. So, for example, you all are sitting here in this room. If you pull your phones out, hopefully if it is on silent, you should find that you are getting a signal, right. Now, if I so let us say that you are sitting over here, right. So, this let us call this the top view, okay, and this is your, let us say this is a window, okay, and let us say there is a door over here, and your mobile tower is somewhere over here, right, which is sending out signals everywhere. Now, there may or may not be a direct line of sight between you and the mobile tower, right. So, for example, if I draw the straight line from here to here, it does not go. On the other hand, there is a path that seems to go like this and then come to you over here. Okay. So, if this were light, would you be able to see the tower? Of course not, right. There is no line of sight, you can't see the tower. But thankfully, it is not light, it is a microwave, and empirically we find that we are able to get reception on our phone over here, even though there is no line of sight. So, there is some idea that the wave is somehow bending around obstacles and we are able to receive it. Okay. So, this is in day to day life. In physics also we have seen this happen. All of us have studied Young's double slit experiment and all of these things in high school, right. So, I mean, the basic idea there is, supposing I have a light bulb over here and I put a slit and a screen over here. Now, if the slit is much bigger than the wavelength of light, okay. So, for example, I take a 100-watt bulb and I put in front of it a barrier with a hole in it, and that hole is, let us say 10 centimeters. So, what is the size of the spot that you will see on the screen? So, let us call this the screen. If this hole is 10 centimeters wide, what kind of a spot size will you see on the wall? Almost 10 centimeters, right. There is no bending happening because it is 10 centimeters, the light will just go in a straight line. So, that is what you see. But when you begin to shrink the size of the slit, right. So, when you make the size of the slit much smaller, right. So, this is your screen. Then what happens is that you observe that there is a interference pattern on the screen, right. You will observe something like this is happening, which cannot be explained if I assume light to be just rays, right. If it were rays, then this is the picture, but this is the wave picture. So, in both of these examples, example 1 and example 2, we get a physical idea that waves are seeming to bend. Okay. So, in school we studied that this is happening because of what was called Huygens principle. Did everyone come across this word in school? Right. So, the idea was that there is a wave that travels, hits some obstacle, in this case the slit, and there are secondary waves that are generated, right. So, if I just draw this over here. So, if I take a light source over here which is sending out waves, so these are the wave fronts, right. When it hits over here, this and these two guys, they become like secondary sources and they start emitting their own waves. So, this is waves from the first guy and these are waves from the second guy, right. And as a result of this, over here on this screen, what happens? These waves interfere, right, and you observe interference pattern appears over here. Okay. So, hopefully this is familiar to all of you, the idea of a secondary wavefront from which now the rest of the once I get these secondary wavefronts, I can forget about the primary excitation, and I get there is excellent agreement between theory and experiment to explain the interference fringes. Okay. So, as you vary this width, that is the other thing you will observe. As you vary this width, you will observe that the interference pattern changes, and that makes sense because I am changing the interference condition, right. The relative path difference is changing as I move the slit around. So, what we will look at in this module is how can we study this Huygens principle, how can we bring it into our current understanding with all the sophistication of Maxwell's equations, and in short, can I study it mathematically. Okay. For example, to this problem, which has your microwave tower and sending your waves to you, can I study it mathematically, and why would that be of interest? Various things. Maybe I am a a telecom provider, and I want to understand under what conditions will all my subscribers get good signal strength. That can be a requirement, right. So, I want to be able to simulate and predict what are the fields given some obstacles. So, that can be a motivation for solving this. So, in short, in this problem, what is given to you? What all do you think is given to you in a problem like this microwave problem? The position of the source, right. So, I have told you, okay, the tower is here. What else should be known? Obstacle. So, the geometry of the room should be given to us, right. What else? Observer, right. So, observer could be anywhere. So, I will try to solve for the fields everywhere, right. So, this is what is given to me. I am given the position of the sources, I am given the geometry, and by geometry, by now we know what do we mean by geometry. Into what is geometry encoded in Maxwell's equations? Permittivity and permeability, right. So, basically epsilon as a function of space. So, this is the backdrop that we should keep in mind as we go towards solving these equations. Okay. So, whenever you get lost, come back to this picture and say what have we solved so far in this picture, fine. Alright. So, now we will go about setting up these equations mathematically. Okay. So, we are going to take a two region problem, okay, to keep things very simple. So, let us say that there is one obstacle over here, okay, and it is inside another medium, let us call this thing over here, okay, and let us say that there are some sources over here, okay. So, let us call this a source. So, this is exactly like our mobile tower problem. J is the location of the mobile tower, and this object over here inside is some obstacle, could be anything, okay. And so, what I will do is I will call this as region 1, okay, and this is region 2, okay. This dotted line that I have drawn over here is the outermost boundary, which actually it does not really exist. So, it is far away. So, let us just call it S infinity. Later on we can study how to bring more and more obstacles into it, but once we understand one obstacle, we basically would have understood everything else. Let us call the surface S over here. Okay. So, this is the problem setup. What differentiates region 1 from region 2 in your opinion? Epsilon, right. Epsilon will be different, that is why region 1 for example can be air, epsilon relative is 1, and this region 2 could be something else, wood, right. So, it is some different epsilon. So, now let us start with, as with any problem in computational EM, we start with Maxwell's equations, right. At the end of this course you will be amazed at how every problem we just start with these 2 or 4 equations and we get a solution, okay. So, these are the 2 equations that I have written. There is your curl of E and curl of H, and the current term comes in the curl of H term, right. So, this should be familiar to all of you by now. Now, what I would like to do is study this, use these equations in this particular problem, okay. So, let us say I want to eliminate from here, there are 2 equations and 2 variables, right. What are the variables? Variables E and H, that is what is unknown, that is what I want to determine, and what is given to me is epsilon and J, right? That is what is given to me. So, let us try to eliminate one of the variables from these two equations. So, let us make it into an equation of one variable. Let us remove the magnetic field. Okay. So, how do you suggest I do that?
Curl of the first equation.
If I take a curl of the first equation, right. So, if I do del cross E, right, we have an identity from vector calculus which tells us this is equal to
Del into del dot E minus del square.
okay.
So we are just like neglecting the chain, the mu chain.
Yes. So, we are assuming that as with almost all real life problems, there are no magnetic materials around. Okay. So, that is why I have taken mu to be equal to mu naught. Okay. So, if you want, we can say in assumptions non magnetic media. Okay. This is not a very fundamental assumption. I can relax it. The math becomes a little bit more complicated, but nothing that we can't handle. Okay. So, we will deal with non-magnetic media for now. Okay. Now, if I try to solve this problem in the most general 3D way, it is going to be a little bit complicated. So, what I will do is I will assume that my problem is 2-dimensional. Okay. So, the entire problem is in the xy plane. Okay. So, what does that mean? What does that tell us about the z coordinate?
Del by del z is 0.
Del by del z is 0, or in simpler words, there is no physics happening in the z dimension. Everything is invariant in the z dimension. So, this obstacle is infinitely long in the z direction, like a tall cylinder, right. So, it also means that all my functions, all my fields are functions of only x and y, right. So, okay. Now, when we deal with a 2D problem, all of you who have probably studied waveguides and such things in your undergrad, you know that we can talk in terms of a general problem can be studied broken up into two orthogonal polarizations, transverse magnetic, transverse electric, right. So, those are the two polarizations that we can talk about, and any general solution or any general problem can be answered as a superposition of Tm and Te. So, may as well solve Tm separately, solve Te separately, right. It just makes life simpler. So, there is transverse magnetic polarization. Okay. Transverse magnetic. So, how do I characterize the fields in the case of transverse magnetic? Hz is 0. So, then Ez is non-zero, right. So, we can say that this is characterized by Ez and what else? Hx, Hy. These are the unknowns in the case of Tm polarization, and analogously for Te polarization, the other sets of unknowns are there. So, what would be the unknowns? Hz, Ex, Ey, right. So, here we are saying Hz is equal to 0, here we are saying Ez is equal to 0. Okay. Now, one thing I want to caution you, this idea of what is called transverse magnetic and what is called transverse electric, you will find two different conventions in the literature. The waveguide people have a certain convention for what is Tm, and people in electromagnetic scattering, they have the reverse convention. Okay. So, you might find it confusing. When they say Tm or Te, just see which of the z component is being set to 0. Okay. So, that is unambiguous, okay, because you might find in some places the other way also. All right. So, to further simplify the mathematical derivation that happens, let us make one more assumption. Let us say that let us deal with the Tm polarization. Okay. Te can also be done, but let us start with Tm polarization. Okay. So, we are going to choose. So, I mean the basic motivation behind all of these assumptions is that our first surface integral equation, we want to make it as simple as possible. Okay. Once you get the hang of it, you can generalize whichever way you want. Now, as a result of this, if I choose the TM polarization, what do you think will happen of del dot E? The divergence of the electric field. So, let us just use the formula. So, this will be, first term will be Ex, Ey, right. TM polarizations, what happens to the first term? 0, there is no Ex. Second term 0, third term 0, right, because Ez is non-zero, but Ez is not a function of z, right. We said that all things are functions of only x and y, right. So, all 3 terms are 0. So, that is great for us, because what happens to this curl of E that I have written over here? Only one term survives, right. The divergence of E goes to 0. So, I have a minus del squared E. Okay. Now, I can substitute this. I mean, this I took the curl on the left hand side. Similarly, I will take the curl on the right hand side as well. So, what will I get? I will get minus del squared E, this from the left hand side, and the right hand side will become minus j omega mu naught into curl of H, and curl of H is j omega epsilon r E plus j, right. So, what I can do is just keep the j term on one side. So, this is the equation that follows, right. So, do all the signs check out. So, minus j into j is 1, right. So, this minus j into j, this becomes 1. I bring this del squared E on the right hand side, and I move this j term on the left hand side, right. So, that is why, so this is the equation that I get. Okay. So, this is called the Helmholtz equation. Some people may call it a non-homogeneous Helmholtz equation, because the right hand side is non-zero. Okay.
The question is for region 1.
This is in general, because I have not made any assumptions, right. Whether this is true for both region 1 and region 2. What happens in region 1? That epsilon r will be for vacuum and current will be there. In region 2, what will happen? Epsilon will be of the object, current will be 0. So, this one equation is true for regions 1 and 2. So far so good? Okay. Also, this surface I am going to characterize by a normal vector over here. I will need that. Okay. All right. Should we go ahead? Okay. So, let's just make it concrete. We had a lot of vectors in this slide. We had a lot of vectors everywhere. Now, because we are dealing with a 2D problem, let us try to just simplify notation as much as possible. Okay. So, this is our geometry again. This is my region 2 with normal over here and surface S, and this is my region 1, and this is my current source J. Okay. So, material properties we have already seen. Epsilon r characterizes the material properties, and this epsilon r is going to be a function of epsilon, I mean it is going to be a function of x and y. Okay. Right. Now, the fields and the currents. So, we are working with the TM polarization, right, for which Ez, Hx and Hy, this is what we said. Now, each of these 3 quantities, I mean they are scalars, right. Ez is a scalar, it is the z component of the electric field. So, it is a scalar function, right. So, all of these are scalar functions. Okay. So, what I will do is I am going to use I am going to denote Ez in region 1 as phi 1 and in region 2 as phi 2. Okay. If you recall, the previous equation was the equation only in electric field. So, that is why I am introducing a simpler notation for the electric field in terms of a scalar. So, I do not have to keep writing vector vector everywhere. Similarly, the current, if I again go back to this equation, the first quantity over here, is it a scalar or a vector? It is a vector, right? Del squared is acting on a vector, it will produce a vector. In what direction is this vector? E is in which direction? Electric field is in which direction in the TM polarization? Z direction. So, the left hand side, the first term is a vector in the Z direction, second term is a vector in which direction? Z direction, bunch of scalars multiplying a vector in the Z direction, so Z. So, it makes sense to also have a Z, a current directed along the Z direction. So, if I take the Z component of this entire equation, that is what I will get over here. So, this J term over here I will write as J Z Z hat. Okay. All right. So, with these simplifications made in place, let us write down the Helmholtz equations for both the regions. Okay. So, region 1, first term was del squared phi 1 r, okay, and then you had this omega squared mu epsilon r, right. So, for all of you know that we can simplify, we can get rid of this mu naught epsilon and write it in terms of speed of light, and that speed of light can get converted into a wave number k, 2 pi by lambda, right. So, once you do all that simplification, I can just condense it into a new constant k 1 squared, that is the wave number in the region 1, phi 1 r is equal to, I will get a j omega mu naught j z r, okay. Just rewritten everything. Region 2, just follow the same recipe. Okay. So, the epsilon, so in other words, this term over here, right, this term. So, omega squared mu naught epsilon r, this is I am writing as k squared. Okay. K may or may not be a function of space, but if like epsilon is a function of space, then k will also be a function of space. Okay. Just I am trying to reduce all the extra variables and condense them into one variable, so that it is easy to see. Alright, so these are the two equations that we have got. Now, we want to solve these two equations, right. So, I mean just looking at these equations, this looks much more complicated than the integral equation that we saw in the previous class, right. So, how do we solve it?